Good afternoon, everyone, or good morning for those of you that are on the West Coast. Thank you so much for joining us today in the latest installment of Talking Tech with SanDirect. My name is Robert Lennon. I am the president and CEO of SanDirect. And for those of you who haven't joined us on these Tech Talks series in the past, these Tech Talks are produced and designed to bring to you the latest in technologies, products, trends, or even general discussions within the data storage industry and marketplace. That being said, today we have a very exciting topic. It's a topic very simplistic in nature that has a lot of complex discussion around it, and that is, how do I pick the right storage for my data needs? A very simple question, but a very complex answer depending on your environment, as well as what you're trying to achieve with your data. That being said, we're very excited to have us with today Gary Watson. Gary is the founder and former CTO of Nexsan Technologies. Nexsan was recently acquired within the last 18 months by iMation, and now Gary is a fellow with iMation. Nexsan, we thought, would be a great partner to be with us on this Tech Talk today, being that their product platform is very flexible within the data center, being that they have products and software that is going to have a broad spectrum of solutions for you. That being said, I hope everybody's enjoying their pizza. Hope everybody has gotten their pizza. We understand Domino's hasn't quite taken over the world, so there is a few spots around the country that Domino's does not deliver to. I'm sure you guys have already gotten gift certificates, and hopefully we can get some lunch to you at a later date. With that being said, I'll hand it over to you. Gary, welcome. Good to see you again.
Thank you very much, Robert. Really appreciate that. Okay. And thank you all for attending this talk, and I hope you enjoy the pizza. What I'm going to do today is maybe a little different than some of the previous talks we've given. I'm going to give you an internal dive into the architecture of the NST family. That's our unified hybrid storage solution. And I'm going to use as an example our NST 6000, which is our latest generation of technology, which is similar to the NST 5000, and I'll point out some differences as we go along. So let's just get started. So what is the architecture of the solution? Well, first thing it starts with is your network. What is your architecture? So first of all, you have probably an IP network, and that IP network might have 1 gig. It might have 10 gig as far as physical layer, and as far as logical layer, you'll probably have maybe NFS for your Unix type clients. You might have CIFS, sometimes called SMB, for your Windows clients, and anything on a Mac post Mavericks defaults to SMB now. So then there's also FTP traffic possibly on that network, and maybe even iSCSI, which is a block protocol. NFS, CIFS, SMB, FTP are file-based protocols. iSCSI is a block-based protocol. All of them go across the IP network. Then you may also have fiber channel. So fiber channel is always a block protocol, and most of you probably have 8 gig fiber channel if that's what you have in your network. But lately we've also seen 16 gig become much more popular. So you have quite a lot of different physical protocols on the network. And so, and maybe you have fiber channel today and you're transitioning to IP, or the other way around, or maybe you're running a lot of NFS today and maybe over time you're transitioning to CIFS. So we wanted to develop a storage platform which would be flexible and would allow you to adapt over time using one set of resources, one set of hardware, one set of software, one set of disks, one set of cache, all of that unified into one solution. And here's how we basically did that. The first thing we have, layer-wise, is a universal interface technology layer. And that allows us to handle protocols like CIFS, SMB, fiber channel, iSCSI, and the rest of them, and some more to come. So a lot of types of protocols. And ultimately, each of those is a separate driver stack, and they all live inside of the box. And I'm going to describe for you initially one of a pair of redundant servers. So an NST solution is delivered to you as a pair of redundant servers. I'm going to talk about one of the two, and I'll show you how the two are linked together as we go on. So, okay, we have CIFS traffic, SMB traffic, fiber channel, iSCSI traffic. And when you break it down, ultimately all of these transactions are either asking to read or write some data. So we have an abstracted I/O layer. So the abstracted I/O layer is taking all these requests in, and it's converting them into a universal internal format. We're allocating storage, we're requesting storage, we're deleting storage, we're doing all that stuff in an abstracted way, so the lower layers don't need to care about whether the request came in as a fiber channel operation or a CIFS operation or anything like that. So let's take the example of write data, what happens. So write data comes in. In the NST 6000, it goes into a RAM-based cache. Now, RAM in the NST 6000, it's actually attached directly to the CPU. It's exceedingly fast, and with the NST 6000 family, the write cache is now standard. You no longer have to buy it as an option like you had to do with the NST 5000. NST 6000, it has standard write cache. And it allows us to do some interesting things. One of the things that it does, and the reason it exists, is as this data comes in from these different types of clients, the block sizes are different. Some operations will be small, 8K, 16K, 32K. Some operations might be megabytes. So what happens is we accumulate these different variable size transactions into a write buffer in the RAM, and some of these may possibly have been compressed because we do offer data compression. You don't necessarily, it depends on your policies you've configured for each of the protocols, whether compression is turned on or not. And we accumulate all these into a nice, convenient transaction size because it turns out that eventually this is going to end up on some hard drives on the back end, and they like conveniently large sequential write transactions as opposed to a bunch of little random transactions. So, here, a few little technical notes about the write cache. Sorry about that. So, the write cache, first of all, it's in RAM. That means two things. Number one, we have to protect it against power failure. And number two, we have to protect that data against some kind of a failure in this hardware stack. So we do two different things to do that. We have a cache vaulting module, which protects the data in the event of a power loss. And there's also a very special piece of technology that allows us to replicate the data in real time to the partner. I haven't talked about the partner yet. There's an identical controller sitting over to the side here that has all the same stuff in it. So what's actually happening is the write cache data in real time is being replicated to the partner controller. And the partner controller has a piece of RAM set aside for that replication to take place. In the olden days, We used to do that using IP networks and other kinds of protocol stacks, which are relatively low latency, or relatively high latency. So one of the objectives of having this write cache arrangement is when your NFS client requests us to take a piece of data, we want to acknowledge that we've received that data as fast as possible. But a couple things have to happen first. First of all, we have to receive all the data in, and if we're going to compress it, we need to compress it. We need to guarantee that data is fault tolerant before we acknowledge to your NFS host that we've accepted that write data. So how we do that is we write a copy of the data to the partner system. The partner system then tells us, okay, I've got the data, and now I can go back and tell your NFS system I've safely received your data. So in the olden days, we'd do this over an IP network or some other kind of protocol. But with the NST6000 family, we're doing something a little bit fancier. We're using a technology called PCI Express non-transparent bridging. So that's a lot. Let me explain what that is. PCI Express, you probably are familiar with. It's the native language that your Intel Xeon processors actually talk. If you look on the motherboard, the actual interface between that Xeon and the various things on the motherboard is PCI Express. But it wouldn't do to simply link the PCI Express buses between the two systems together, because that would allow a risk of some problem on one system interfering with the operation of its highly available partner. We can't have that happen. Non-transparent bridging is a new technology which is effectively like switch zoning, which allows us to zone which areas of PCI Express the systems are allowed to talk to. In our implementation, we only allow the system to write to its specifically allocated piece of redundant storage location. So the neat thing about it is it's the native language of the processor. This is running on a big Xeon with maybe 16 cores. It's very high performance. We use two quad links. The throughput is something like 16 gigabytes a second, and it's got microsecond type latency. So the latency is exceedingly low. The bandwidth is very, very high. And as I say, it's the native language of the Intel processor. So I don't have to, like, for example, convert it to InfiniBand and then send it over to an InfiniBand link and then convert it back, right? So it's a very natural protocol to use. PCI Express NTB is only something that just very recently became usable in this type of an architecture. So that's what we use to do the replication. So as I mentioned, we've got the data, it's come in, it's into the write cache. We've accumulated it into a nice, reliable, replicated, battery-backed up write cache. So what happens to it from there? Well, it doesn't necessarily immediately go to disk. It sits in the write cache for a little while we decide whether or not it's ready to go to disk. If it needs to go to disk, we'll flush it to disk. I'll come back to that point in a minute. But what it may do in the meantime is, based upon our caching algorithms, it may be promoted to what we call the L1 read cache. L1 read cache is another piece of RAM which is dedicated to very high performance read cache for your most frequently used blocks of data. If it gets evicted from the level 1 read cache, we then have a level 2 read cache, which is actually flash memory. So we have RAM here. RAM is the fastest, it's the lowest latency, but RAM is relatively small and relatively expensive. Flash, on the other hand, we have in the NST6000 family, we have 48 slots to plug in flash devices. Currently, we're supporting a maximum of about 10 terabytes of level 2 read cache in flash. So conceivably, you could have a very, very large amount of read cache. The write cache, in contrast, is on the order of 16 gigabytes. depending on the model and the configuration. Give you a sense of scale, okay? So, and I'll come back to why these are significant in a few minutes. So all of this lives inside one controller. So the next layer that we talk about is we have a storage abstraction layer, which is storage pools. So the storage pools are a very convenient architecture which allows you to not have to deal with individual RAID sets or that level of granularity. This is the main aggregation system where we aggregate large numbers of physical RAID sets into a logical RAID set, into a logical pool. So the write data will come eventually, it will get flushed to the pool, and then will be flushed outside of the chassis into some kind of physical hardware on the back end. Now, because we're Nexsan, we have a lot of choices as to the physical hardware on the back end. Let's take, for example, you might have one of our E60 VTs. An E60 VT is a box that holds 60 hard drives. So what does that mean? So you could have 60 4-terabyte drives, for example, at 7,200 RPM. So that would be a high-capacity system. That's 240 raw terabytes. And just based on the way this E60 VT works, that might work out to, let's say, 7 or 8 physical RAID sets. But as an administrator, you don't want to have to manage that, right? You don't want to have to deal with all those individual RAID sets. So as you add this device, when you first set the system up, it'll say, would you like to just stick all that into one big pool? That's what most people do. They'll just take that shelf, they'll take all those RAID sets, and they'll just throw it into a big pool that's abstracted. But you don't have just that choice. You could make mini pools. You could buy more storage shelves and make a gigantic pool. In fact, the maximum amount of pool storage on the back end of our system is 5 petabytes, 5,000 terabytes, and probably bigger by the end of the year. So we do offer some pretty large configurations. But 7,200 RPM drives are not your only choice. And by the way, there's some bigger ones coming. It's 4 terabyte today. 6 terabytes are just around the corner. So the capacity of these systems are getting enormous. But we also offer a lot of other choices. We have a 32 bay box that holds 2.5-inch drives for higher IOPS configurations. We have we allow you to use 10,000 RPM drives. We allow you to use 15,000 RPM drives. We can even put a shelf of drives on the back end that's all solid state, if that's what you need. We consider that kind of a 1% corner case kind of situation, but a shelf of SSDs is something like 170,000 IOs a second. So you can get quite a lot of different choices on the back end. As a practical matter, what you normally will do you'll group together similar types of storage shelves into one pool. You won't mix 10K and 7,200 RPM drives in one pool. It doesn't make sense. You'll put your 7,200 RPM drives in one big pool, and if you have SSDs, you'll make a separate pool out of those. And as you allocate NFS shares, CIF shares, and so forth, you decide what pool you want them taken from. Do you want that CIF share coming out of your SSD pool because it's super, super critical performance? Or is that maybe a backup target, and so you want to use your most economical, highest capacity tier? So the neat thing is this is all done through one simple pane of glass GUI. You don't have to think about these layers of what's going on in the back end. It's all done for you. Another choice we give you, most people, as a practical matter, when they build a system like this, they'll use RAID 6. Just because you get dual parity, a lot of protection against hardware failure and so forth. But there are applications, for example, we have customers who use this for video backup storage or as a Commvault target or something like that, where they don't necessarily need the high availability of RAID 6. They want to lower the cost per terabyte a little bit. So they'll use RAID 5. On the other hand, there are situations where perhaps if you're using SSDs or 10,000 RPM drives and your objective is high IOPS, you might want to use RAID 10. All of those are available. You can have all of them simultaneously in the same system. You can have some NFS shares with one policy and maybe FTP with a different policy. We allow you to do that if you want to do that. So one of the things about hard drive arrays, there are a lot of systems that have unified storage, but one of the things they all seem to share is this idea where the 16 cores we have available to manage these protocols and the file system also have to deal with all the RAID stuff. They have to do the RAID calculations. There's a lot of housekeeping with hard drives. If a hard drive fails, you have to do a rebuild. You have to do surface scans to make sure they stay healthy and so forth. One of the things that's interesting about our technology is the storage shelves have their own low-cost, low-power storage controllers in them that handle all those low-level functions. So in terms of RAID calculations and disk rebuilds and surface scans and so forth, we're not wasting or interfering with your front-end processor power by making the front-end processor deal with those things. So as you add these shelves, you're adding more and more of that processing power without detracting from the processors that are used to implement CIFS, NFS, FTP, the file system, and so forth. So I mentioned this is an active-active system. What that means is, I mean, I know that there are systems out there where they have dual controllers, but the second controller, which is a duplicate of the first one, it doesn't do anything. It's idle. You know, it's like dead, and it only comes to life in the event that the first one fails, which really should be, you know, 99.999% of the time, it should be working. So all of our products these days are active-active. What that means is the partner controller is also available. All of its processors and RAM and everything are also available to service I/O at the same time. So both of them are running at the same time, and they cooperate a little bit just so that they can share a little bit of their RAM to back up each other's write cache. But apart from that, they're operating independently until a failure occurs. If a failure was to occur, the surviving controller will take ownership of all of this cache and all of these pools and will service that data transparently up to your hosts. So the intention is this is meant to be highly available. Now, failing over such a complicated system with a lot of cache and a lot of shares and so forth is very, very complicated. And when we first launched the product, it took a couple of minutes up in a very large system to actually fail over. Then we got it down to 30 seconds with a bunch of work, and now we're well below 30 seconds to do a complete failover of a multi-petabyte system. So the failover time on these systems is extremely low. Hopefully, with the reliability we build into the system, it doesn't happen at all. But if it were to happen, it happens very, very quickly. So, and the neat thing is, both of the systems are serving workload for you. You're getting utilization out of both of them at the same time. So what's happening? Why is it architected like this for reads and writes? So obviously we want high throughput. So for high throughput, we have lots of ports. There's lots of 10 gig ports or 8 gig fiber ports or 16 gig fiber ports on these two controllers, And the controllers themselves are built with the latest high-performance Intel processor technology, very, very fast PCI Express Generation 3 controllers. The throughput through the system is very fast. The throughput down to the back-end storage is very, very fast. Lots and lots of SAS 24 gigabit connections down to the storage. But throughput's one thing. Latency is really another thing that's very important. Latency is the round-trip time between the time your FTP client or your NFS application asks me for a piece of data. So hopefully he's going to ask me for a piece of data, and it's going to be either in my write cache, which I check first. If it's not there, I check the level 1 read cache, which is in RAM. If it's not there, I check the level 2 read cache, which is the flash. If it's not there, I go to the back-end storage and get it. And so, you know, we hopefully, if we have a high cache hit ratio, your latency will be very, very low, sub-millisecond if it's in any of the caches, and just a few milliseconds if it's on the hard drive arrays. And latency on writes is also very important because your application, it has a list of things to do, and it wants to write this, it wants to write that, it wants to write the other thing. And the neat thing is because the writes actually go into the write cache and are replicated to the partner very, very rapidly, the write latency tends to be well below a microsecond because it's simply writing to RAM and then ultimately flushing it to the back-end storage. So let's see, what else can we talk about today? We've covered basically how the stack works. I will talk for just a second about the difference between this is the NST 6000, and our lower end models, the NST 51 and 5300 model. The main difference, they all work the same, the software is the same. The only real difference is the write cache on the 5000. Instead of using the RAM inside the controller, actually is a plug-in device that is visible. It's like looks like a hard drive. It has RAM and a battery and flash inside of it, and you have to buy it as an option, and it becomes a fast tier write cache device. It has to be dedicated to a specific pool, and it's a good solution, but it's faster than using flash for that application, but it's relatively expensive. With the NST 6000, using the RAM that's in the processor, it's much, much faster, and we no longer have to worry about using a plug-in device for the write cache. So everybody gets to get write cache. Now, the read cache, the level 2 read cache, is optional. If you have an application where either the performance is not critical, or you know for a fact that it's not a cacheable workload, let's say it's a backup target, where caching is irrelevant, you may decide not to bother to buy any of the read cache devices. You don't have to. You're not required to. There's 48 empty slots. You can add them later. If your requirements change, and at some later point you decide, hey, I want some cache, you can buy those cache devices, plug them in hot, and it'll say, hey, I've detected this new read cache device. What do you want to do with it? You assign it to whichever storage pool you think is interesting, and then that's that. And in fact, in the next release of the code, we'll even let you split it between storage pools if that's what you want to do. So it is a very flexible solution for caching. There are workloads that are not cacheable, so we don't make you buy it if you don't need it. Okay. Cacheable workloads tend to be business applications, and certain types of video applications like transcoding are very cacheable. VMware, any Hyper-V type application, file server applications, those are all very nicely cacheable, and the cache hits are very, very good. And the cost benefit of sticking in some of that cache is very, very effective. Let me cover one other point, which I think is interesting. So we're using RAM for write cache. We could have used a flash device of some kind for write cache. A lot of people do. The issue you have is flash devices wear out. So there's basically three types of flash. Let me just talk about that for just a second. So one type of flash, well, first of all, there's RAM. I'll talk about RAM in a second. But let's talk about the three types of flash. So you have single level cell, you have enterprise multi-level cell, you have MLC, and then there's some new technologies kind of in the 3 or the 4 level MLC. So what's the main difference between them? A single level cell device can usually withstand a couple of 100,000 rewrites on every flash sector before it wears out. You do the math, basically says if you pound on this thing for 5 years, it'll probably not wear out across a reasonable lifetime of a normal application. Enterprise multi-level cell was anywhere between 10,000 and 100,000. 10,000 is a little too low. If you're using it as a write cache device, it's probably going to wear out in 6 months or a year or something like that. And by wear out, I mean fail. You know, it has a finite amount of lifetime. It's like charging and discharging a battery. In fact, that's literally what it's doing. And it will wear out and die. But the latest generation of enterprise MLC is up in the 100,000 territory now. So if you pick the best enterprise multi-level cell, we find that that's reliable enough to be used in our L2 cache. We have not found a flash-based technology which has enough lifetime to be used for the main write cache. So we're using RAM for that. RAM has the property of having an infinity lifespan. So you can write to it as much as you want to. And as a matter of fact, the read and the write speed is symmetrical. It reads and writes at the same speed. These different flash devices, the read and the write performance are very, very different. You might find that an MLC device can do 20,000 IOPS read and 1,000 IOPS write or less. And how many IOPS it can do depends on what you've been doing to it lately. So if you write to it a lot, it'll run at 1,000 IOPS for a while, and then suddenly it will drop to 100 IOPS or 10 IOPS or some almost zero number while it stops to do what's called garbage collection. So you can get some real nasty surprises with some of the higher density, lower cost flash devices. That doesn't stop some vendors from selling them, but we have found that MLC is basically the flash that's inside your iPhone, right? It's very, very good for read, and it's good for writes occasionally. It's good as a drive inside your Apple laptop, but it's not durable enough or performant enough to be used as a caching device. It might possibly be good enough for the back-end storage in some situations, where the writing is not very intense, where the writing is infrequent and is done in conveniently large chunks. But so far, we have not, at my company, been able to qualify any MLC devices. We keep looking at the new ones as they come out. There's a new generation that have just come out that may possibly be good enough for the back end. You know, but so we're very cautious. We use the RAM for the write cache. That's the most demanding part of the application. It's where we need the most performance, lowest latency, infinite durability. We need it not to care about small block sizes and offset blocks that are variable sizes that are not aligned. We don't need it to not care about any of that. So we tend to use RAM for the write cache, and either SLC or the best EMLC for the L2 read cache. So We do a lot of things to make the system more reliable. We try to make sure we're only using the right kind of flash technology and SSD technology where it fits. We don't force you to buy SSD when you don't need it. The SSD we provide is the correct reliability for the application that you have. We allow you to not buy read cache if you don't need it. So, we give you a lot of flexibility there, but if you want to really go all out with performance, you can have a lot of RAM, a lot of flash, and even have an all-flash backend if you're really, really on the high end of speed and performance. But we also let you have capacity levels in the petabytes. We have many multi-petabyte sites running the NST system. And there aren't very many, if any, completely universal host I/O unified storage systems that allow you to scale to those kind of sizes, and very few of them allow you the kind of flexibility we do in terms of selecting the different types of hard drives that go in the back end, in terms of allowing you to pool your storage in the way that suits your requirement. So that's basically a quick summary. A nice unified storage solution that everything's inherently thin provisioned, zero impact snapshots, all those nice features that you're accustomed to, with as much solid state as you need for your application, where all of these resources are shared between all the protocols, so it is truly unified with one pane of glass for management, built-in asynchronous replication, a whole bunch of other features I'm not going to go into today sales pitch wise. I just wanted to show you how the thing is hung together. With that, I'll just like to say thank you all for joining us today. I know I sort of went through this really fast, but I wanted you to have a quick view of what's inside an NST 6000. And with that, I'll turn it back to our hosts at SAN Direct. And,
Gary, thanks so much. Appreciate it. Thanks for coming in. Thanks so
you.
much. We had a handful of questions, or a lot of questions actually, that came through with the registration. I think Gary did a fantastic job at answering pretty much all of them. If there was some that cropped up after the fact, or if there was some more that you had during this presentation, certainly feel free to give us a call, 866-463-3372. Our storage architects will also be following up with you as well, just to see if you have any more other questions and just kind of get your general take on the presentation and some of the technology we went through today. Thanks again for joining us. We appreciate it. We'll see you next time on Tech Talks.